Okay, before I do anything here, I see that I have to go, before I'm sharing, I see that I have to go and bring up an Excel file, the one that I mentioned to you, that is not opened yet, so it'll be a smoother presentation later. Okay, so here you go. I'm showing here, I'm starting with just reminding you the single parameter change. And from here, we'll go to multiple changes. It's an analysis, sensitivity analysis on a single objective coefficient. I added the word single here because it's not going to be single later. I did not use the word single objective coefficient before because by definition, sensitivity analysis is doing it only for a single coefficient. Either one coefficient of the objective function or one right-hand side of a constraint. But now that I'm going to add a second and third coefficient, it becomes a different issue. That's why I added the word single. And I just want to remind you what is it that we have been doing and go from here. So for convenience, I denote the source by the letter S and destination by the letter D. And what happens here is a single change. The unit transportation cost for the good old transportation problem that we solved last time, from source 1 to destination 3 is currently 7. So x13 has a coefficient of 7. But this coefficient is increasing by $3 per unit. It's happening because maybe the gas prices went up and now unit shipping cost is increasing. So on this particular coefficient, it becomes 10. And so the question is, should the shipping plan change because of that? If it's more expensive to ship a unit on this route, why ship 10? This is optimal right now. Maybe it's not optimal anymore. So sensitivity analysis will answer the question right away. The allowable increase of 7 is up to 11, but it's moving only to 10. So because 3 is less than 4, it's the change fall inside the allowable increase. And therefore, the optimal solution remains the same. So the plan of transporting items from sources to destination, as you see it here, does not change. This makes it possible to recalculate how much it will cost you very easily. It will cost you what it used to cost you before. And if you remember the run, we ended up $540 on the previous solution that calls for this. But now you're paying $10 instead of $7 on the same quantity. So you have $3 increase times 10 units, and this gives you the optimal cost. If you changed in the input this 7 to 10 and rerun solver, you'll get a new total cost that will be equal to 570, but the transportation plan will be the same. So this was the first thing that we mentioned last time. Then I'm showing another change. They are not occurring together, each one separate. So now the unit transportation comes from source 1 to destination 2, from source 1 to destination 2. So it's this value is dropping by 1 unit. So now it's a little bit cheaper to deliver or ship units on this route. And the same thinking is maybe we could increase this 15 to 16. Well, the answer is no, because a decrease of 1 is less than allowable decrease of 16, as you see it here. The optimal solution does not change, and the total cost only becomes cheaper by $1 acting on 15 units shipped. And this is it. So now we get the total cost. So that's what I want you to see on the single objective change. Now things are changing. I'm defining here to you a procedure how to run the multiple objective coefficient changes. Multiple, that's why I call it simultaneous. They are not occurring one at a time. If the gas price is increasing along route 1 to 3, why is it not changing to all the routes? So multiple changes is something that is happening all the time. Multiple changes are very typical, and if sensitivity analysis is limited to one change at a time, its contribution to decision-making is very limited. Comes the new analysis and extending the single change into multiple changes under a certain condition. And that's what I want you to see. So you can read it here, but it's better to look at the following example that demonstrates what's on the previous slide. I'm showing to you an example of simultaneous changes of two objective coefficients. The objective function therefore has x1 and then x2 and maybe more variables. But I'm focusing on the two coefficients that are changing. C1 is the current value of x1, of the coefficient of x1, and C2 is for x2. So they don't have to have the same value, but if you remember the sensitivity report, when you ask for it, Solver generates for you a range of optimality in the form of allowable decrease on the left, allowable increase on the right for each one of these coefficients. So that's what I show here. Now you are told that delta 1 is a decrease in the value of coefficient 1. Delta 2 is an increase of the coefficient of C2. And the question is the same as in the single coefficient change. Is the optimal solution going to change because of these two together? It's not that they are occurring one at a time. Notice that if they were taking place one at a time, each one alone is not causing any change in the optimal solution because it falls inside the allowable decrease here and inside the allowable decrease increase here. The question is what happens when it's together. The way to analyze it is to form two ratios, one for each change. The first one is the delta 1 from here divided by the allowable decrease. Don't forget to write negative here. And the reason is the delta 1 is already a negative value. You want the ratio to be positive. Excel or Solver does not place the allowable increase as a negative value. It's a positive value there, but it's called decrease. So you translate it. You say delta 1, and you divide it by the negative of the allowable decrease. The ratio now is a positive value. And then comes delta 2. Here you don't have to make any adjustment because this is positive and this is positive. You divide them and you get a positive ratio. When you add these two positive ratios, the question is it more than 1? If it is less than 1, no change in the optimal solution will occur. That's the rule. If it is equal or to 1, you don't know. It's questionable. If it's greater than 1, almost 100% of the time, there will be a change in the optimal solution. And even when it is equal to 1, only when it is less than 1, when the sum of ratios is less than 1, then there will be no change in the optimal solution. Here's an example. We have an objective function with 3 variables. So we have 3 coefficients. All the 3 are changing. The first 2 are increasing by 10%, and this one is decreasing by 10%. So you have a new objective, 8 plus 0.8, 5 plus 0.5, 7 minus 0.7. It's a new objective function. The question is the new objective function optimized exactly at the same location where the old objective function was optimized? To answer this question, you look at the sensitivity report. I generated out of my head some hypothetical increase, allowable increase and decrease. So C1 can move up by 2.6 and down infinite. It can go to any lower value. C2 can move up to any value, but down only by 7. That's the allowable. And here is another. So now you create what I called SR. No one else is calling it SR but your professor. I made it up, and it means sum of ratios. So you take the first one, which is 0.8, and you divide it by the allowable change in the same direction, which is the increase. You take the second one, 0.5. Again, it's an increase. You divide it by infinity. And here you have a negative 0.7. So you divide it by the negative of 1.2. This one gets off the window because it's already equal to 0. So you add the first and the third one, and the sum is 0.89, and this is less than 1. Conclusion, because it's less than 1, the optimal solution that you got from the first objective, you will get from the second objective. No need to rerun to know that. So that's the rule. It's called the 100% rule. I don't call it, it's the sum of ratio rule that tells you if the optimal solution on simultaneous changes will change or not. And the changes are in the objective coefficients. Now I go back to the transportation problem. Apply this rule to this. So to remind you, we have 2 sources, which are production plants, and you have 3 demand points, and a commodity is sent from the production plant to be sold at the 3 cities. Each city has its own demand, and each plant has its own capacity. They are equal to one another. You have 50 units capacity here and 50 units demand here. So all the demand can be met and all the constraints become equality. We talked about it last time. For this problem, we ran and obtained an optimal solution and the sensitivity report. And now I'm going to use the sensitivity report to do simultaneous changes. So the 2 simultaneous changes for the objective coefficient are C13. It's the coefficient of the variable that is called X13. It is the transportation from source 1 to destination 3. This C is increasing by $3. So I'm repeating the same question as before. But at the same time, C from 1 to 2 is decreasing by $1. So now I combine the 2 separate cases from before into one case. Is the optimal shipping plan going to change? See, the same question that we asked before, we ask now. Now, delta is the change of the coefficient. Ij, it's the coefficient. C sub ij is changing by delta. So I'm calculating ratio. For the route from 1 to 3, I take the delta I3, that is now 3. I divide it by the allowable increase, then it's now 4. I repeat the same for the decrease of the second coefficient. So you have -1, and then you divide it by -16, and you add them. You add them, and you get -1, less than 1. It is less than 1. Conclusion, those changes do not cause any change in the optimal solution. So in spite of this one, becomes more expensive almost by 50% per unit. And this one is dropping a bit from 16 to 15. This goes from 7 to 10. Goes 16 to 15. Still, this plan is optimal. Keep doing what you have been doing, but the total cost is not going to stay. So now for the total cost, and this is the second question here, you just take the original function. You know that the optimal solution is the same. You can use it. And then you add to the original value of the objective function the changes due to the changes in costs. So here's the objective function. It's 540. This is the first change plus 3. It's here. And it is applied to 10 units that are shipped. Here is a decrease of $1 applied to 15 units that are shipped. The total is the new total cost. And that's how you deal with multiple changes for objective coefficients. Now, the same thing, I want to move to changes, to simultaneous changes of the objective function, but the cases are just more extreme, and I want you to see that. No different than the treatment of the previous questions. So take a look. There are 3 simultaneous changes. I want you to see that the work that you did before for 2 changes can work for 3, 4, or 5, it doesn't matter how many changes. They are all changes of objective coefficients. So C from 1 to 1 is increasing by $5. This is the one, and it becomes $19. Quite more expensive. But C from 2 to 2, so it's here, that's from source number 2 to demand number 2. This one is decreasing by 50 cents, and the other one, it's from 2 to 3, it's here, it's also decreasing now by $2. Question, what happens to the optimal production plan? Transportation plan. So delta 1 is positive, 2 is negative, 2 is negative. Take a look at the ratio. First one is here, 5, and it's an increase divided by infinity. And then -1 here divided by 0. And the last one is -2, and then it's divided by 4. At this point, you don't even have to continue. You already know that the sum is more than 1. And that's because the one in the center, when you divide by 0, you get infinity. So the sum is already more than 1. The conclusion is the optimal transportation plan is not going to stay the same. Therefore, for the question of recalculating the total cost without the need to rerun, the answer is impossible. You'll have a new production transportation plan. You must rerun if you want to know what it is. In fact, common sense, when you see these 3 changes, you don't even have to turn to the multiple changes at all. Because when you look at the one in the center here, right now it's 10, but the allowable decrease is 0. For the solution to stay the same, you cannot drop 10 to any value below it because the allowable decrease is 0. Once you drop it, you already know that you're going to get a new optimal solution. So the other changes don't matter. You will get a new optimal solution just because of this. The formality is this. It's not a mistake to do. I'm just telling you, you could know it right away. So that's about simultaneous changes for objective coefficients. Now, sensitivity of the right-hand side, starting with a single change, a review of what we did before. Okay. So now we are focusing on the lower part of the table because this is where the constraints are. And the right-hand side, when RHS means right-hand sides of the constraints. So let's assume that the supply from source number 2 increases by 3 units. What will happen to the total cost? Single change. Only one constraint right-hand side is changing. That's only an introduction to the simultaneous changes. I'm looking for source number 2, and I see that the supply, which is the right-hand side of the constraint, increases by 3 units. Formalities call for checking the allowable increase here, which is 5. So you have 3 compared to 5. I'm staying within the allowable increase, but this time is the range of feasibility. And therefore, the shadow price here for this change remains -6. The shadow price. Wait, here. The shadow price remains -6. Okay. Yeah, here. So will there be any change in the optimal solution? Well, if you have been using all the capacity, and you see it here, and I'm getting 3 units more here, then I'm going to use them because the shadow price is the contribution to 1 additional unit. And the shadow price can be used because the change is within the range. This means that when you place here 23, you are going to use all the 23 units from this source. But then you are going to ship the 23 units from this source. And so the shipment plan from before is changing. So immediately you know that this solution does not remain optimal. But the good news is, in order to know what is the new total cost of the new transportation plan, you don't have to rerun it to know. Why? Because you can use the shadow price for that. So you take the old total cost, which is 540. Then you make the change plus the shadow price, which is -6, plus the supply change, which is 3. So I call it delta of supply number 2. And this is equal to, and this change is 3. So the overall change in the total cost will be savings of $18. The solution is preferring to ship more than from source number 2 than from source number 1. If it has 3 units more, it will use it. So it's, and why? Because the shadow price is negative here. So these shipments are more efficient than the first source. That's what you can learn from such an analysis. And this was a single change. Now I'm going to the simultaneous changes. 2 constraints are changing at the same time. So the first supply change as before exists, but management realized that the demand number 2, which is here D2, this demand is expected to drop. Let's say they realize that next week there is some holiday in New Orleans, and therefore the demand for the product is going to drop. And they estimate the drop will be 2. So now we have 2 changes. Can we use shadow prices? We apply this sum of ratios rule from before, only that before it was applied to the objective function. Now that it is applied to the constraints. Exactly the same way, exactly the same rule. So this delta is 3, And this delta is -2. Yes, from 3 and from here. Divide the 3 by 5 because it's an increase. Divide by allowable increase. Divide the -2 here by -15 because this one is a decrease. Add them and you get a sum that is less than 1. The conclusion is that the shadow prices will not change. And before it was that the optimal solution will not change when you did the sum of ratios. Here, the whole question is about the shadow prices. They don't change. So if they don't change, you can use them in order to recalculate the total cost, no need to run. The total cost new is the 540. And then the first shadow price is -6. The change is an increase of delta by 3. Multiply. Then the second shadow price is 16, but the demand is a decrease of 2. Both give you savings in the total cost. The first one is because you can ship more efficiently because you can balance your shipments in a way that you couldn't before the supply increased by 3 units. And the second one is because before you needed to meet 15 units demand, and now you can meet only 13. So you can ship smaller number of units, so you can save money on transportation cost. So that's the case of simultaneous changes on the right-hand side. The two of them are doing the same. You look at the actual change and you divide by the allowable change of the same direction. Positive, positive, negative, negative. For the objective coefficient, the optimal solution doesn't change. For the constraints, the shadow prices don't change. In both cases, you can recalculate the total cost, use the old solution. And that's what the multiple changes topic, you see, it's quite simple, it's doing, and that's what I would like you to be able to answer. So that's the simultaneous changes. When you solve problems from the book, you will not see the simultaneous changes per se. It will give you one change at a time. Create your own practice. You see that as constraints have changed. You know how to answer it based on shadow price. Add another constraint of your own to the change. Ask, can I tell that the shadow prices are changing or not? If not, can I calculate the total cost? Do it. That's a good practice. Once you do it once, you will control it. You will master it. It's very simple. And I'll give you some more questions of the same type after we are done in the next few days, I believe. Okay. I'm back at the transportation, and there are some cases of transportation that I want to raise because they are very, very, very practical, and you will find them if you will ever happen to use the transportation model. Transportation regularly is dealing with very large geographical areas that are covered by a set of, say, plants, factories, stores, and manufacturers that have to ship, like you bring a shipments of some commodity to the port of San Diego, and from there you have to ship it all over the country. And there are a variety of ways how to do it. So for the transportation case, it's very expensive, those transportation costs, and sometimes you add to them the production cost in the plant as part of the transportation cost. And production costs are different than from plant to plant for a variety of reasons. And so suddenly it becomes more expensive, the whole plant. And the question is, how many to produce in each plant and then ship it, and where to ship it to? And you have 5 plants like this. So the problem is very interesting, very large, and the costs are very, very, very expensive. Now, in addition to that, suddenly you have routes that are blocked for weather conditions, because of some construction that are done that either eliminate the route altogether or reduce the traffic to half of what it used to be. Your solution called for 20 trucks a day on a different route, but reality is you can ship only 3 because of those restrictions. The transportation model per se does not include those restrictions. We have to add them. It's very easy to add in one way, but there are better ways than others. And I want you to see, first of all, what happens if a traffic along a certain route is completely blocked. This will be one thing. The other one will be what happens if the traffic in a given route is reduced to a maximum allowed. That's the second thing. And the third one will be when the problem is unbalanced, when the capacity is smaller than the demand. So by definition, you are going to have shortages in some of the demand points. I think we saw last time how to adjust the model to a case when it is unbalanced. Today, I show to you what happens when you can evaluate the shortage in shortage costs. And this is for an unbalanced model. So these are the 3 things I would like to do today, and then we'll see how much time we have, if at all. Okay. So I'll start with the last one, which is the shortage. And I'm hoping I'll have time to go to the Excel and show to you how. If not, then next meeting I'll do it. But here is the story. The original problem had 10 units demand in St. Louis. I changed it, demand in St. Louis has increased to 20 units. The capacity could not be adjusted. You cannot just change capacity in one day. So now management can produce only 50 units in all, but they can only meet 20 units of demand. 10 units will remain in short. So we are creating here shortage. Now, in this case that I'm adding information to what we had before, the shortage cost can be evaluated. In different cities here, when there is shortage, the market responds by penalizing you, the supplier, differently. $13 is the estimate of shortage cost per unit in Des Moines, $7 only in Kansas City, $11 in St. Louis. This is kind of an analysis that is done by the accounting department, by an economist that you hire. So you have this data, and now the question is, okay, if I can evaluate the cost, maybe I don't want to create large shortage in Des Moines because the shortage is so expensive. So you can add those shortage costs to your transportation costs, and it will affect your transportation plan now. And how do you do it elegantly? Add a new supply called shortage. Call this shortage. You pretend you ship the shortage. You pretend. You even know how much it costs you to ship a unit in short. For example, shortage that is shipped from this node to this node will cost you $13. That's the shortage cost. If you include this in your shortage transportation plan, you know that you create a shortage of 1 unit in Des Moines. And now you have to add $13 to the transportation cost. And that's what you do to all of them. This is node called normally a dummy node. It does not exist. You add it mathematically. Why? Because now you can solve the problem as a balanced transportation problem. The actual transportation costs come only under the red arcs. These are additional costs under the shortage. The only interesting thing here, what will be the supply? These two has a supply. What supply do you put here? It's a non-existent supply point, but you know that this is the shortage. So the shortage is 10 units because there is a shortage of 10 units created if the demand is 20 and the supply is only 50. No, the demand is 60 and the supply is only 50. So you have here a shortage of 10. That's what this node is going to provide. And you solve it as a transportation problem. Solver doesn't know that the cost here is not a real transportation cost. For solver, it's a cost. And it minimizes the sum of everything. But you want everything be minimized because you can evaluate your shortage cost. You just add it to the transportation costs. So that's a very simple, elegant way of overcoming the case of unbalanced problem when supply is less than the demand, creating shortage, but shortage costs can be evaluated. If shortage cost cannot be evaluated, it means that you cannot include those costs in your model. So those costs will be considered 0, 0, 0, and 0, and go ahead and solve the problem again. Now, it doesn't matter what the shortage is because they're worth the same. So all what the model will do, minimize the real transportation. That's another elegant way of overcoming an unbalanced problem when you have shortage, but shortage costs are not included in the model. Just plug in 0. And that's what you do when you have an unbalanced problem when the demand exceeds the supply. Now, I don't want to go to the assignment. I'll go first of all to the Excel file and demonstrate on the Excel how do we solve the problem, and then talk about how do we block routes, something I didn't show to you here. Okay. You should be familiar with this page because we were there before. I just added a few pieces of information here and you can see what it is. I'm dealing with the limited traffic. That's the other issue. And how do you block routes? And when the demand exceeds the supply, I just finished that. Okay. First, to remind you, we have a linear programming Excel file for our transportation problem when it is balanced. It's completely balanced, and I have from before something that I'll delete at this point. I'll edit later. I don't need it. This is the original model. Here you have 2 supply points, 3 demand points. Here are the 2 supply constraints, the 3 demand constraints. I'm just reminding you. And the total supply, which is X11 plus X12 plus X13, is represented by these 3 ones. Sum product is the sum, cannot exceed 30, being the capacity of S1. And the same for the capacity of S2. But now the ones are here, 1, 1, 1. So for the demand constraints, you don't want to ship less than what the demand is. And you know that you can because you have enough capacity. So you write greater, greater, greater than, or equal to. And you add the 2 shipments that goes from each one of the supply points to the demand point number 1, both here and here. And you get that it has to be at least 25, and then 15, and then 10, and you place the 1 in the proper place. Okay. And this was the original model. The only comment I have here, I advocated writing here equal, 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 and it is correct because it's a balance problem. But even if you write less than or equal or greater than or equal, you'll get at the end an equality. How do I know? It's the minimization mechanism that is trying to ship as little units as possible. Well, then it will not ship to the demand point more than 25 here, although you allow it. And it will not ship more than 15 and not more than 10. You allow it, but it will take the 25, 15, and 10 because you allow it also. So this will be equality here. This means that I shipped exactly 50 units, but then I shipped in 50 units, then I have to ship out 50 units. And the only way to do it is to ship 30 here and 20 here. So all the constraints will be equality at the end of the day. So I could write equality, I get the same solution. Now, with this said, I want to solve the problem as a linear programming model, and I already have the function, the sum product here and here. I don't want to repeat it again. And you enter it in Excel and you get the solution. I want to go to a different formulation. The one that is more popular for the transportation, and then you'll see next Tuesday for the assignment, for network problems in general, it's more popular. And here's why. The reasoning is both practical and convenience. Suppose you have, I'll make it small, only 3 plants in 3 different cities. Fine. And now, but you have 11 different markets. And you have to ship to all the markets from each plant. The number of variables you are going to have will be 33. 3 by 11, x11, x12, x13, x11, x21, 2 11. You see? 33 variables on one page is a little bit too many. It doesn't go on one page. And in a real life problem, you don't have only 33 variables. You can have 200. The number of routes expands tremendously. So you don't want to organize everything in one line like I did here. See, one line, and make it long from here and forever. It's better if we can organize it in a tabular form. That's where I'm heading. Whenever you have data that can be organized in a tabular, a rectangular manner, do it, it's better. All the variables then will go in a matrix. I take this data from here that is linear, not linear, in one line, and this one should be actually 16. So what I do, I organize it in a little table, D1, D2, and D3, and S1 and S2 here. So then I copy the data from here, 14, 16, 7, you see? 8, 10, 5. Don't make a mistake here. Check to see. This one is the cost from 1 to 1. So you put it here. And this is from 1 to 2. Then you put it here. And that's it. Organize the data. Then take this table and copy and paste it here. Same table. Okay, copy and paste. Delete those values from the here. Delete it. Keep it empty. Okay. Now, these will be your variables. So when you go to solver, don't report to solver those variables here. Report these variables here. So if you have 3 by 11, it's quite easy to put it in one table and report this easily to solver. You highlight the table and that's it. Now, the variables here will be x11, 2, 1, 3. These represent shipping from source number 1, and the sum of shipments will be here. So enter the function sum here. And you see sum of what? Of the first row. In the second row, it should be the shipments from source number 2. You can just copy this function one row down, or you can just type it. So here's the second one, see? This gives you the total shipments from each source. As a reminder for yourself, copy the sign of these two, you see, both are less than or equal to, and then right here, the capacity. And then you'll enter this as a constraint. You'll enter it as a constraint to solver. Do the same to the columns. Columns represent shipping into the demand point. X11 and X21 is what is shipped from the two supply points to demand point number 1. Sum them here. You need the sum. So you take the sum of this column. Now copy it here. You have the sums of the second and the third column. For yourself, write greater than or equal to and the demand. Enter it in solver as follows. In class, I would not go and show you to do. I will ask you first to do it yourself. And then we'll talk about if somebody made a mistake, I'll do it on the board and you will correct it. Here, I have to make a shortcut. So I'll delete everything. I want to do it from the beginning. Objective function. Okay, so the objective function, I forgot to say, it's here. For the objective function, use some product. And the reason it's the most convenient function. Instead of typing yourself, 14 times N8 plus 16 times O8 plus, do it 6 times. Instead of that, do some product. Enter the first matrix and comma. Enter the second matrix and close parentheses. Do not press F4 like we did here to fix the values of the variables. We don't need it here because you use some product once in the whole model. Now I'm ready. I'm entering the objective function as O14. It's here. It is minimized. The variables now, don't forget, you are using the variables and then you use them for the constraints and the objective function. So highlight the correct cells for the variables. Then you add supply constraints, the two shipments from the supplies not to exceed the capacities. Now, add here demand constraints. 1, 2, and 3 are the actual demand satisfied, cannot be less than, therefore change it to greater than or equal to. And now the actual demand here. So you enter this. And okay. Non-negativity, yes. Simplex, yes. All what we need is to solve the problem and we have a solution. The optimal solution here is 540, which is what you would get if you were solving it with solver before in the previous formulation. Okay. So if you have a larger problems, this is how you want to set it up. This is really showing that you understand the linear programming. This is showing that you know how to read the report. And the report is easy. Ship 5 units from S1 to D1, 15 units from here to here, and so on. It's very easy to read. Also, you see immediately where you don't ship. And There is more things to say when you look at the sensitivity analysis. I'm not sure I'll have time to do it today. So I'll do it next time on this problem because I want to do sensitivity analysis, additional one, on one aspect of it when it comes to multiple optimal solutions. And then I go to assignments. That's what I think I'll do. But right now, I want to go to blocking routes. It's very common in transportation, as I said. And first I show to you what is the easiest way to understand it, but not the one recommended. So take a look. Let's assume that the route that is blocked is from source 1 to destination 2. This route is blocked. And currently, from 1 to 2, you are shipping 15 units. So now you have to find a new arrangement that will not use this route. In other words, you want to push the shipments on this route to 0. It's not that you cannot find an optimal solution without this route. You have many options, but you want the optimal solution to not take x12 and make it equal to 15. You want to make it equal to 0. You can add a constraint to the problem. And it's x12, so I'll add it here. What do I do? x12 equals to 0. I'll add the number 1 here. I'll continue the sum product to calculate its value. If this was 15, you see 15 here, because this is what it does. 1 times 15 plus 0 all across, then you get 15 here. And this has to be equal now to 0. You see what you do? You add a constraint to the problem that is strange to the transportation problem. It's an external addition to the transportation problem that forces no shipments on this route. Very easy to do. So why do you even talk about it? Here's why. You don't want to add such constraints to a large-scale transportation problem. Even one constraint that you added will destroy the algorithm that is solving that. These algorithms that are very smart know how to work on very large-scale network problem, including transportation, but they require that the set of constraints will be exactly what you see here on the diagonal. You see it on the diagonal, you have once, and you have once, and then you have once, and it's all diagonally based. Mathematically speaking, this is what they need. The rest are zeros. It's some ones, zeros, diagonal. That's what is required for those algorithms to work, and then they will give you an optimal solution in no time. Even if the problem is huge, the solution will come up very fast. Once you interfere with this structure with a constraint that looks like this, that does not belong in this structure, the algorithm doesn't know what to do. So you try to avoid it. And there is a very elegant way of avoiding it. I will not interfere with this constraint at all. If I could do it by adding a constraint to the problem that meets the requirements of these diagonals, I would do it, and these algorithms will not suffer. Because I cannot, I will do it in a different way. I will not touch the constraints, although it's all about one constraint. So that's what I want you to see. It's done all the time. This is not the way to go. But I'll turn to this formulation, and it's very easy to do it here. If I don't want any shipment in this cell here, it means that I don't want solver to put any shipments here. I want it to put the value 0 there. I'll force solver to do it by placing here a very expensive unit cost. That's all. That's why you saw 1,000 there before. This is not the original problem. But hey, we don't have the original problem. We have a problem where solvers have to find optimal transportation plan going around this unique blocked route. This way, I guarantee that it will not be optimal for solver to place any transportation here. If this is 1,000 and you put even one here, 1 unit, you already added, what is it, $10,000, $1,000. So when we solve the problem now, you see, I don't change the model. The model is the original model. I change one objective coefficient. Look, this 1,000 forced the shipments here to be 0, and the rest were optimized. And guess what? The cost is exactly what we got before, which means there is another transportation plan here that gives you the same minimum cost. Transportation is notoriously known to have many optimal transportation combinations with the same minimum cost. The only problem is to find the others. So solver does not give you the others, but there are indications in the sensitivity analysis how to look for them. And this is a point I want to make next time, just to complete the discussion on the sensitivity analysis. It's a very interesting topic in linear programming in general, to find multiple optimal solutions that not always exist. But I want you to see what is the indication in the sensitivity analysis that helps us figure out another optimal solution. Here, I just gave you one. These shipments are not the shipments that were there before, and still I have the minimum total cost. So this is almost the last topic for today, and the rest of it is how do you reduce transportation in a route not to 0. If you reduce it and it's not going to 0, you can't put a huge number here to prevent it, because you don't know which number to put there. So this is not as simple as it looks. I can do it on this formulation. This is done. You have to add what we called before a dummy supply. So there is something to explain here, and I need time for that. So I'll take you back to what is not preferred, but very intuitive to do for us. Let's assume the transportation, okay, here you have 10 units. I don't want more than 4 units shipped from source 1 to destination 3 because there is limited traffic allowed on this route. Which means I want this variable to not be more than 4. Well, I can go back to the previous method. I'll put 1 here. I'll put here less than or equal to, and I put the value 4. So now x13 will not be more than 4. See? I'll add this constraint to my formulation in solver, not the one that you have now, not the one that you used to have before, the original one. And solve the problem, and this will make it. It's not very typical to do in transportation problems, so I'm hoping I will be able to do all this next time. So next time, I want to go on 2 topics with sensitivity analysis. 1, multiple solutions. I'll show to you just 1 visit of that. The other one is how to reduce the traffic on a route to a certain level. And then the rest of the time we'll do assignments. The assignment is the problem that is very similar to transportation. I would like you to see it. It's already on the PowerPoint ready for you. And with this, I finished my today's class. Okay. Okay. Any question?
You're saying that there's an assignment due?
Can you raise your voice? What do you say?
You're saying that there's an assignment due?
No.
Or just practice assignments for us?
I'm not adding any assignment.
Oh, I thought you just said that right now. Sorry.
No.
Well, you think you'll be able to have that like study guide exam 3 that I mentioned
I'm
to you?
working on it, and I hope within a day or two I'll finish, because I want to have there a few linear programming examples of all those that you need to get ready for. And I want to include the transportation, including sensitivity questions. So I'm hoping in each question to include sensitivity. That's what the book does, by the way. You have a lot of sensitivity questions in the book. You had a chance to take a look?
Yeah.
Yeah, the book doesn't call it sensitivity, but I'm telling you, now that you know what sensitivity is, it is. It's sensitivity analysis. And he asked you about changes, possible changes. The only thing, he's doing it one change at a time. And he is not referring to the ranges of optimality, range of possibility to know if there will be a change in anything. He just wants, if he has more than one change, he wanted to rerun it with solver to tell. Not a big thing to do. No, I want you to know the sensitivity. So you can add sensitivity question to yourself, not even wait for me. I am working on a study guide kind of that will cover all this, because in the test, I want on, first of all, inventory. And I want inventory you to know the EOQ with quantity discounts, which we didn't do yet. We did the production and we did the cycle service level, but we didn't do the quantity discounts. I will include it in the test. I think it's the easiest of the three. So that's one thing. Then in linear programming, you need to get ready to all what we covered, not saying that everything will be in the test. Maybe we have 6 different applications, maybe 2 will be in the test, maybe 3. There is a time limit here that you have, and I cannot include all of it. So you have production mix. It was the first example. Then you have them in the book too. We have the financial investment problem. We had the advertisement marketing problem. We have the personnel management problem. Remember the question on the graphical designers, that it was Lisa and David and Sarah were, and the question was how many hours to apply. So there is such an example.
Yes.
And then there is the transportation, the blending problem, the transportation, and the assignment that you will see next week. So all those, and just if you practice them by the study guide, or even by the book, they have those examples in the book, then I think you should be ready. What I want to ask you to do is to set up a linear programming model without a solution for, say, 2 of the possible problems. Like I do on the PowerPoint, I set up the model first with the objective and the constraints, just write it down, type it. You have to type it and send it back. And then you will have a sensitivity report from me that you don't have to run. So I'll give you a model, I'll set it up for you, and then give you the solution for that model. And you'll see sensitivity report, print it out. You don't have to run it. What you need is to understand what's in the report and answer questions about what you see. It can be multiple choice questions about different things in the report, and you have to select the correct answer. So some minor calculations there in order for you to know the answer, and this is it. That's the sensitivity report. So that's the component. Now in inventory, it will be just like, I think the assignment is a good demonstration. Even the quiz, it was about the inventory. Then you see what I'm doing. I give you, say, one quantitative calculation question and some multiple choice question. Overall, look, you have 110 minutes, maybe 20 questions, of which 3 will be calculation, the rest will be give or take. I don't know yet. I have to write the exam, then I'll decide. But this is the structure that you should expect. 3 computational, the rest will be multiple choice or close to that. I hope this gives you some idea. Okay?
Sounds good.
Flora, where did you take your picture?
I had a do-over.
Huh?
I had to use my wife's computer because the one I was using shut down on me.
Ah. You are ashamed of your own face. You put your wife there. Uh-huh.
Oh, this is her laptop.
It's her laptop. Yeah. Full with the reasoning. Okay. Okay, so that's all for today. And I have to end the meeting if I want to stop the recording.
All right, thank you.
Bye.